We left off in our previous video talking about the Bohr model and that light is quantized, but that Niels Bohr was only able to get his model to work with hydrogen. So let's take a second here and see what we've come up with, and then see what Bohr was talking about and what he actually was proposing. So we have that the wavelength times the frequency is equal to the speed of light, and we also have that the energy of light is equal to h nu, or hc over lambda, and that light is quantized, which means it can come in certain size packets that we call photons, and that light has both wave and particle characteristics, which we call wave-particle duality. Now, Niels Bohr's model of the atom was that you would have this positive nucleus, and then outside of it you would have different energy levels that he called orbits, where the electrons could be. And sorry, my circles aren't very good. But they would be these orbits at different levels, and that the electron would be able to move between these orbit levels, either by gaining energy or by losing energy, and that each one of these energy levels would have some energy E sub n that was based on a number, minus 2.178 times 10 to the minus 18 joules, multiplied by 1 over n squared, where the n was this integer from each of these levels, and the E sub n is the energy for each of these levels. Okay, so when an electron is gaining energy, not electrons, another word starting with an E. When it gains energy, then it increases n level, and it gets further from the nucleus. And we say that this is an excited electron. When the electron loses energy, then it would be decreasing in n, and it gets closer to the nucleus. And when it does this, we say that it relaxes. Not relation. I can talk and write at the same time. No, I really can't. Relaxation. So we can say that it undergoes excitation or relaxation. So electrons can get energy from several different sources. They can absorb light. They can get it from electricity. They can get it from a collision with another molecule or atom, and from a chemical reaction. And this probably covers most of the different ways that electrons can get energy. Maybe there's some more, but those are the main ones that I can think of right now. So when this electron goes between energy levels, we say that it undergoes an electronic transition. And we would describe its energy as a change in energy. And it will be the final energy minus the initial energy, just like when we do change in temperature. And so if we look at Niels Bohr's model, we said that it matched up with the Balmer model. So let's take a look at how that works out. So let's remember the Balmer equation a little bit. So remember that Balmer had this equation 1 over lambda equals r 1 over n1 squared minus 1 over n2 squared. And we remember that for n2 was equal to 3 and n1 was equal to 2, we got a wavelength of 656 nanometers. And now, since we have the equation E equals hc over lambda, we can understand what the energy of a photon is going to be based on its wavelength. So we can go ahead and calculate the energy for this wavelength. Okay, so you can pause the video and give this a try, just based on 656 nanometers. I'm going to go ahead and write it out. So there's my Planck's constant and the speed of light. And then 656 times 10 to the minus 9 meters. So when you do this calculation, you should get 3.03 times 10 to the minus 19 joules. Okay, so here's our baseline. This is the energy that was being emitted. So this is red emitted light. So if the Bohr model does the same thing as the Balmer model, then the idea is that our change in energy should be the energy for n is equal to 3, that was this one, minus the energy for, oh, excuse me, it's the other way around because we're losing energy. So our final state would be in the E2 state, and then the initial state would be in the E3 state. So let's calculate the energy difference based on the Bohr equation. Remember that the Bohr equation says E is equal to minus 2.178 times 10 to the minus 18 joules times 1 over n squared. And this is just for some energy level that's specific. It is not the change in the energy level. So when we do the change, we need to subtract them. But notice also that this same constant is going to be in both of them, so we can factor this number out first. So we can have this change in energy be minus 2.178 times 10 to the minus 18 joules that we're going to factor out of our 1 over 2 squared, that's 4, minus 1 over 3 squared, which is 9. So this probably is looking a little bit familiar, right? Over here, it looks a lot like this setup for the Balmer equation. And in fact, when you calculate this through, you get exactly the same number. Okay, so we already talked about the fact that Bohr's model only worked for hydrogen, but so did the Balmer model. So they were obviously missing something important. And long story short, the thing that both of these models were missing is that when you have atoms that have, well, if we think about hydrogen, right? We know that hydrogen has 1 proton and 1 electron. From looking at the periodic table, we can see that it is, its atomic number is 1, and it has to have 1 electron in order for it to be neutral. So a neutral hydrogen atom in H1 would have 1 proton and 1 electron. So the atom has 1 proton and it has 1 electron. And this electron, when it's here by itself, it has a relatively straightforward way of changing energy levels. So the problem is all other atoms have more than 1 electron. And we know that charges repel each other, right? Like charges repel. And electrons can move. And this gets complicated. This complicates the math in trying to describe this so much that there is no simple equation for trying to describe it, the behavior of the electrons around the atom. And this is true. There are no simple equations describing the interaction of electrons in any other atom. Hydrogen is the only one that we can describe exactly. All of the other ones are too complicated because of electron-electron repulsions. Oops. Again, I keep trying to talk and write at the same time. Complicated. Okay. So the other thing that was missing from Bohr's understanding actually mystified the scientific community for a couple of decades. There had been quite a bit of work done, and then it all stalled out for about 20 years. So fast forward later, I forgot to write down the date for this, but I think it's late 1920s. And we have a young graduate student named Louis de Broglie, and he's thinking a lot about light and how light has this wave-particle duality. And he thinks to himself, what if electrons also have wave-particle duality? What if they can act like a wave? Because remember, electrons have been assumed to be particles. They have mass, they have charge. They're not like light, right? And so everybody just assumed they were little round spheres with negative charge on them, effectively. So Louis de Broglie looked at Einstein's famous equation E equals mc squared, which is where we can relate the energy of something with the speed of light and its mass. And this mostly gets used when we look at the mass conversion of nuclear particles, which we'll be doing next semester. And he said, well, since this is working at the speed of light, let's just pretend that light has a momentum. And we'll just call that P. This is momentum. Momentum is defined as the mass times the speed of something, okay? And so this isn't a weird conversion. This is just a totally straightforward one. And he said, okay, well, light also has energy that's based on its wavelength. So these two equations, maybe we could set them equal to each other because they both are energy, right? So then we'd have hc over lambda is equal to p times c. Notice that the speed of light will cancel out for both of these things. And he said, well, this means that you can talk about the wavelength of something in terms of Planck's constant divided by its momentum. And if we were talking about the wavelength of light, then this would get us some light momentum, which we don't really know how to deal with right now because light doesn't have mass. But electrons have mass. So let's calculate the wavelength of an electron using the mass. The mass of an electron, we haven't talked about this in a while, but I'll just remind you, it's 9.109 times 10 to the minus 31 kilograms. And we probably do need to keep it in kilograms instead of atomic mass units because Planck's constant is in joule seconds. And I don't think I've mentioned this before, but joule is this combined unit of kilograms meters squared per second squared. And most of the time we don't really care about this because things cancel out. But if you actually want to see how they cancel out unit-wise, then you have to be able to see all of those bits in here. Okay. All right, so let's say, what if the electron has speed of about maybe 2,000 kilometers per second. This is a reasonable speed. They can go faster than this too, but it's quite a bit slower than the speed of light. It's like less than 1% of the speed of light, just for context. So let's calculate the wavelength. All right, so 6.626 times 10 to the minus 34 joules seconds divided by the mass, 9.109, times 10 to the minus 31 kilograms. And the speed is 2,000 kilometers per second, so we'll say 2,000 times 10 to the 3 meters per second. So if you want to see what the units are doing, joules, I said, was kilogram meter squared per second squared. So on the top, we've got kilogram meter squared per second squared multiplied by seconds divided by kilograms and meters per second. So if we look at how that's going to cancel, one of these seconds cancels here, the other second cancels here, 1 meter cancels here, 1 kilogram cancels here, and what you have left is just meters, which is what you want for wavelength. Okay, so what we get is a wavelength that is about 3.6 times 10 to the minus 10 meters, or if you remember, that's 0.36 nanometers. So what we need to know now is this something that is reasonable for us to be able to detect on one hand, and also would this change how an electron can behave? And the answer is yes and yes. We can detect things on this scale. We have to use X-rays to do it, but we can do that. And the other thing about it is that this is about the size of a chemical bond. Some chemical bonds, anyway. So this is absolutely relevant to a wavelength, or excuse me, to an electron. So this would be a noticeable wave-like effect. Okay, so notice though that this equation, oh, and I should mention to you that this is called the de Broglie wavelength. Notice though that the de Broglie wavelength can be calculated for anything that has momentum. So does that mean that anything can have a de Broglie wavelength? Well, I guess theoretically, but let's look at how big it is. What about a human being who happens to be running, so they have momentum? Let's calculate how big it is. So let's say that we have a human who is, I don't know, about 150 pounds, okay? Sort of medium-sized person. And we're going to have to convert that into kilograms. There's 2.2 pounds per kilogram, so that turns out to be 68 kilograms. And then I'm not a very fast runner, so I'm going to go with kind of a slow speed. I'm going to imagine that they can do a 10-minute mile. So let's say that they're kind of cruising on this slow jog. For some of you, it's probably slow. This would be 6 miles per hour. I can't run this fast, but maybe someday. Okay, so in 1 hour, we have 60 minutes, and in 1 minute, we have 60 seconds. I'm doing these unit conversions because I need my speed to be in meters per second and my mass to be in kilograms, just like before. And then in 1 mile, you have 1609 meters. So if you do this calculation, you get 2.68 meters per second for this person's speed. So let's calculate their wavelength, their de Broglie wavelength. So we still have the Planck's constant on top, 6.626 times 10 to the minus 34 joules seconds. Then their mass was 68 kilometers, and their speed was 2.68 meters per second. So notice that these numbers are really small, and so they're just going to make this small number on the top even smaller. So if you do this, you get 3.6 times 10 to the minus 36 meters. And minus 36, as far as 10 to the minus 36 meters, this is so much smaller than anything that we can measure. So remember that atoms are about 10 to the minus 9 meters in size. Maybe even a little bit smaller than this. But this is like so many more zeros smaller that it's not even comprehensible to me. I don't even know. Nobody can measure this. So if you are running, you might have a de Broglie wavelength, but nobody can measure it because it's too small. So we can't prove that you don't have a de Broglie wavelength because it would be too small to measure. So I think the way that people tend to think about this is that electrons and light and small atoms, just atoms in general, they are very small. We call them quantum sized. And anything in this quantum world does not behave like things in our macroscopic world. Okay, so since electrons and atoms and light don't behave like macroscopic things, it means that the way they behave is really hard for us to understand. And that's okay. We don't have to be able to sort of visualize it, but it means that we're going to use a lot of analogies. So hopefully everybody is going to be comfortable with the idea that we're just going to have to use a lot of analogies. And so we do say that electrons and other small things have wave-particle duality, just like light does. And by the way, Louis de Broglie, he proposed this in his PhD thesis, and I can't even imagine the stress of proposing some new physics theory in your thesis. And then it was proven, sometime in the next year, and then he was given the Nobel Prize like 2 years after he got his PhD, which is crazy fast work. All right, so the other conclusion that we have from all this quantum stuff is that we need new equations. We can't model electron behavior and atom behavior using our old physics. So instead, we developed new equations, and there's a couple of big issues here, big ideas. We have Heisenberg's uncertainty principle, which I'm mostly not going to talk about in this class, but I'm happy to tell you about it if you're curious. And the other big one that we will talk about quite a bit is Ervin Schrodinger. He developed a set of equations, and these are specifically wave equations. So he decided that since electrons could behave either as particles or as waves, he was going to go ahead and model them as waves. And so his set of equations are called wave equations, and we mostly don't need to worry about his equations either, but we are going to use Schrodinger's equations to visualize what atoms are like in terms of their electrons and in how to understand their bonding. So this is what we will use to both visualize atoms and molecules and understand how and why they bond. So we're going to go into these visualizations next, but I'm going to go ahead and put that in a separate video. So I hope you have enjoyed learning about this brief, very fast history. There's a lot more really cool stuff to learn about the history of the development of our understanding of the atom. So I hope if you're curious that you look up more articles, and I can send some your way as well when you have time and energy.